Hi, I'm Barsha Radhakrishnan and I'm going to present my project for image processing, which is analysis of Sobel nonlinear filter and Gaussian linear filter. Firstly, we analyze the difference between linear and nonlinear filters. This will help um, designers in real time to manipulate image information and extract the data that is if the most effective manner using the latest image filtering technology. The differences between linear and nonlinear filters are very pronounced. Linear filters tend to blur edges on the image details, while nonlinear filters preserve edges and are difficult to design. The edge detection is a technique that is implemented by one of the ways we can implement is using a Sobel filter, and it is carried out by using the convolution method. Convolution of an image uh, by using a kernel filter. What is called a kernel filter is a 3 by 3 integer or n by n integer in which is smaller than the image, and that convolution is carried out throughout the image in the horizontal and vertical directions. Gaussian filters are linear low-pass filters, and they modify the image by convolving with the Gaussian function. So here in Gaussian filters, the kernel is the Gaussian function. And in this project, we see that um, MATLAB functions are MATLAB codes are simulated to implement both filters and find out their various intricacies and also where each is implemented and most effective. We also come to a final qualitative conclusion and based on performances of each in the presence of noise. Today's technology has removed a lot of limitations on complexity of filtering techniques in real time and embedded image processing, and analyzing these differences is one of the um, applications of this project. Sobel operator or the Sobel filter. In the Sobel filter, we we use a mask or what we call the kernel, which is an n by n cross n window for convolution. The convolution that we do here is with the entire image, and here the image is assigned a value from each pixel is assigned a value from 0 to 255, and the uh, the Sobel edge detection algorithm uses four operators of this kernel. The output obtained is measured for intensity variation in all directions. The Sobel operator is a column mask and a row mask, which means that we will have outputs across both directions, and that will be conjoined to form a final image. That is the Sobel output. The result of the column mask is the horizontal difference, and the row mask is the vertical difference. When an image is captured by a camera or any other imaging system, uh, it can be afflicted by poor contrast or variations of illumination. And we need uh, image processing for noise reduction and interpolation. This is where our filtering techniques come in. And this paper will highlight two major types of filtering. And we've seen one already. Gaussian filters are motivated mainly by the uh, possibility of noise reduction. and it's basically taking average. It's the next step to average the averaging process. The averaging process would entail um, taking a lot of images and just averaging them to get the output final image. The next best thing to remove noise is the replacement of each pixel by a weighted average of the neighborhood pixels. So this causes smoothing of the image, and the smoothing also essentially does the averaging process, averaging of the image of the pixels, and the visible difference it gives is the seemingly single point of light that when viewed through an unfocused lens looks like a fuzzy dot and that is made to look like a square. A more prudent method would be to eliminate the effect of the edge, just like in Sobel, and check the weight contribution of neighborhood pixels. This is where other filtering techniques, when implemented along with certain techniques, are helpful, which in due course we will see it will is advantageous for us. So these filters remove the high frequency components, or in other words act as low pass filters to the image. So the larger the sigma value, that is the standard deviation, the more details are removed. So the convolution must be implemented as the reduction quadratic to the linear, and the figure is like superimposed grid. So next we will get to the MATLAB simulation of the various functions that we can do, processing that we can do on an image using these two algorithms. The kernels that we use for the Sobel operator are this K1 and K2. Both of them are horizontal. This is the horizontal kernel and this is the vertical one. And we can notice that their sum is 0. This ensures that when the kernel passes over an image, the pixels that differ in intensity from the neighboring pixels will be multiplied by the non-zero values to get again non-zero values. But when the kernel passes over a region of uniform intensity, then the the sum will give us a zero or close to zero value. So this is where if, the zero value is blacked out and the white lines that we see in a Sobel output is the non-zero values. So we can first of all um, the Sobel output can be obtained by just inputting an image, and this is the horizontal and this is the vertical kernel that moves across the entire image, and we get the output here. Um, so the Sobel output essentially is the uh, edge detection, where these are the non-zero values that we saw earlier, and the blackened regions are the uniform regions, which are the zero values. This actually is the output from the horizontal filter alone, the horizontal kernel alone. This is from the vertical, and this is a combined image. And we also have um, a normal Sobel output from that shows very clearly the 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 Sobel the work of a Sobel filter, which is shown here. As we see here, the threshold is very high to show exact edges of the image. This is the Sobel filter. This is the call, and this is the function for the Sobel filter. Next, we see the Gaussian curve. Here is the code for a normal Gaussian curve, and we see that this is the curve and the mesh version. This is just to show the kernel, which is in our Gaussian function. And next we see the blurring of a Gaussian that is caused by the Gaussian function. The blurring effect is seen here from the original image. This is a function of the sigma value that or the standard deviation, and we can change the value of sigma. If it's a very small value, say 10, we see that more blurring occurs, and for a higher sigma value, say 50, the blurring is very less. So we have analyzed the Sobel and the Gaussian filter, and in case of a noisy image, we we know that a Sobel filter is good to detect the edge in where the noise is very less in the image, but in the presence of noise, we see that the Sobel filter is not so good. Instead, a Gaussian filter can be implemented, or processing with a Gaussian filter can be done to make the output much better. And under the conditions of various sigma values, as we saw, uh, we can obtain better outputs when pre-processed with the Gaussian filter in the case of a Sobel filter. So this is the classic case of the use of one filter for the effectiveness to increase the effectiveness of another filter. This is the conclusion and our results for the project, and these are the references. Thank you.